Hello everyone. In this chapter we are only covering the first section. So chapter 7 is the normal probability distribution. I really just wanted to cover the basics with you in this chapter. We start right off with an illustration here. It says, suppose that United States Parcel Service is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable, capital X, represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could be at 10 a.m., x equals 0, or at 11 a.m., x equals 60, with all 1 minute intervals of times between x equals 0 and x equals 60 equally likely. That is to say, your package is just as likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. The random variable, capital X, can be any value in the interval from 0 to 60, so that it is greater than or equal to 0 and less than or equal to 60. Because any two intervals of equal length between 0 and 60 inclusive are equally likely, the random variable, capital X, is said to follow a uniform probability distribution. A probability density function, or a PDF, is an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. 1. The total area under the graph of the equation over all possible values of the random variable must equal 1, and the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. The graph shown to the right illustrates the property for the time example. The area of the rectangle is 1, and the graph is greater than or equal to 0 for all x between 0 and 60 inclusive. Because the area of the rectangle is height times width, and the width of the rectangle is 60, the height must be 1 over 60. Values of the random variable capital X less than 0 or greater than 60 are impossible. Thus the function value must be 0 for capital X, less than 0 or greater than 60. The area under the graph of the density function over an interval represents the probability observing a value of the random variable in that interval. The probability of choosing a time that is between 15 and 30 minutes after the hour is the area under the uniform density function. So you can see if we mark off and just choose from 15 to 30, shade that in blue, the probability of it being between 15 and 30 minutes would be that 15-minute segment divided over the 60 total minutes in that hour, or 0.25 or 25%. Relative frequency histograms that are symmetric and bell-shaped are said to have the shape of a normal curve. So this illustration here is a normal curve. A continuous random variable is normally distributed, or has a normal probability distribution, if its relative frequency histogram of the random variable has the shape of a normal curve. In other words, it's bell-shaped and it's symmetric. We call one standard deviation out above and below the mean the inflection point. So the illustrations here at the top show two different examples at the top. Our mean equals 0, our standard deviation equals 1. That's the left-hand tan shaded curve. The blue shaded one that overlaps it, the mean equals 3 and the standard deviation equals 1. At the bottom, a somewhat more condensed example. So at the bottom, for the mean equals 0 and the standard deviation equals 1. And then that's the tan one, and then the blue one, the mean equals 0 and the standard deviation equals 2, and you can see how those fall together. So to recap some properties of the normal density curve. It's symmetric about its mean. Because mean equals median equals mode, the curve has a single peak, and the highest point occurs at that at that mean or median or mode. It has inflection points at 1 standard deviation above and below the mean. The area under the curve is 1. And the area under the curve is split in the middle at the mean. It is a half for the area to the left of the mean and a half above the mean. As x increases without bounds, so as it gets larger and larger, the graph approaches but never reaches the horizontal axis. Just the same way as x decreases without bound, the graph will approach but never reach the horizontal axis. If we go back to the empirical rule, remember that 68% of the area under the normal curve is between 1 standard deviation above and below the mean. 95% within 2 and 99.7% within 3. And here it is graphically represented just like in that chapter when we covered it. In this example, it says the data on the next slide represent the heights in inches of a random sample of 50 two-year-old males. Draw a histogram of the data using a lower class limit of the first class equal to 31.5 and a class width of 1. And do you think the variable height of two-year-old males is normally distributed? So here we have our values of the heights of 50 two-year-old males. So we tabulate those, put them in categories, and those categories are going to run with one point intervals on the horizontal axis. So the first one starts at 31.5 and it goes up to but doesn't include 32.5. The next one starts at 32.5 and goes up to but not including 33.5, and so on. We plot all those values. Looking at this, I would say this is a fairly normal curve. There's little deviation in it. It looks like a fairly normal bell curve. In the next slide, we have a normal density curve drawn over the histogram. How does the area of the rectangle corresponding to a height between 34.5 and 35.5 inches relate to the area under the curve between these two heights? So here's the illustration of that normal curve over this histogram. If we look at the heights between 34.5 and 35.5, you see where that falls in correspondence with the mean and how it somewhat peaks at the top outside of that normal curve. Suppose that a random variable x is normally distributed with mean and standard deviation. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristics described or the probability that a randomly selected individual from the population will have the characteristics described. In this example, the weights of giraffes are approximately normally distributed with a mean equaling 2,200 pounds and standard deviation equaling 200 pounds. It wants us to draw a normal curve with parameters labeled, shade the area under the normal curve to the left of x equals 2,100 pounds, and suppose that the area under the normal curve to the left of x equals 2,100 pounds is 0.3085. Provide two interpretations of this result. So we carry over that information at the top. The mean is 2,200 pounds and the standard deviation is 200 pounds. We plot that out in this bell curve at the bottom. We mark the 2,100 or less, shade that in. The proportion of giraffes whose weight is less than 2,100 is designated by the point 3085. The probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085 or 30.85%. Okay, so that wraps up section 1 of chapter 7. That's all we'll be covering in this chapter. As always, let me know if you have any questions.